Assalamu alaikum. I welcome all of you to the course on basic concepts of chemistry. Today we will be studying hybridization. We will be discussing that what hybridization is, okay, and another portion of this course is that why hybridization is important. So why a molecule tend to hybridize, it is a little bit advanced topic, and we'll study that in the next advanced lecture section. So what hybridization is, this is the main topic. So let's start from some example and you will understand that. Suppose we have a methane molecule CH4, this is called methane molecule. Many experimental evidences about these molecules are previously known. That is all CH bonds are same. Okay, they are all of the same length. Number second, what evidence is known? All CH bonds have same energy. Okay, now there is another evidence which is related to the geometry of the methane molecule. Third, the angles between all CH, theta between all CH is 109.5. okay, now the angle is 109.5. all bonds are equal in length. All CH bonds, I mentioned the CH bonds, they have the same energy, same length, all CH, and the CH bonds, they have all CH bond has 109.5 degree angle between them, so that make it a tetrahedral. Let me draw a tetrahedral. After a while I'll try to make you understand that what tetrahedral is by using some models, but let me try it because that's what the experiment says. Okay, these are all CHs. This is called tetrahedral. The middle, this thing is carbon. Okay, let me write it. Right, now again all the angles, the angle between this hydrogen and this hydrogen is 109.5. this hydrogen, this is 109.5. this hydrogen and this hydrogen is 109.5. As I mentioned, that it will be clear to you by seeing the model. This one, all CH bonds are at 109.5 degree to each other. Okay, so that is the information which we have. So let's write it on board in a small space. Okay, what information we have and why I am telling you and why it is important, you will see it in just a moment. CH4, all CH are equal in length and energy. Angles between all the CHs, let me just draw two, that but you will see these are HH is 109.5 109.5 degree. Okay, this is the information we have. Now let's start. Let's come to the central atom, which is of course the carbon, and carbon has electronic configuration of 1s2, 2s2, 2p2. As we write it in an open way or in the more old classical way, which majority of the people write 2s, it has 2 electrons in it, and 2p has, let me write the 2p as 1, 2, 3, 3, okay, they have 2 electrons in it. So it has just 2 unpaired electrons. So according to the basic theories, that unpaired electrons are those which can make a bond, as you saw in the hydrogen atom, because in a hydrogen molecule both hydrogen has 1s electron. Okay, I am right, this is nucleus and this is the 1s electron, and another has, this is positive nucleus and this is the 1s electron. So unpaired electron mean that these unpaired electrons were used to form a bond. But when we look to the carbon atom, it says that the electronic configuration, it says that it can just form 2 bonds. Just two, because it has 2 valence electron, and those bonds will be formed between the 2 p orbitals. Okay, the p orbitals will form the bond with the hydrogen, and S is filled, so it doesn't need any bond formation because it is stable in itself. But but according to the information given by experiments which people knew, was that carbon can form 4 bonds. So we are discussing methane right now, okay? But the methane, the experimental evidence is that methane has 4 bonds. Where the fourth, how the 4th bonds could be? Okay, so let's say that this is the ground state, okay? Ground state means normal atomic ground state, and with some heat or something, this carbon is excited. Excited means that this place is available, so the electron can go and it can come back. Okay, so let's the electron jump into the above orbital 2p. This is 2p. Sorry, I haven't written on it. Now what is there? 2p. Again 1, 2 and a 3, 1, this is our 2s, okay? 2s. 1 electron is left here, and all the electrons are like this. As you might have studied the Hund rules and Pauli exclusion principle, etc., that if you have same energy electron orbitals available, then each electron sit single. First of all, they will be occupied singly, and each electron will prefer single orbital, and they should be its direction should be the all should have the paired direction. Okay, so the parallel direction, in the same direction they should be. Okay, so again, now one thing is very okay. Now according to the concept of bonding, this thing can now form 4 bonds. This thing can form 4 bonds. Okay, but 4 bonds with whom and with what? Okay, so let's see, let's come. We have an orbital which is called S2s. Okay, simple 2s orbital. I'm not going into its lobes or anything other than nodes, lobes, etc. It's simple 2s orbital. This is writing very bad. I think that okay. And two p orbitals, as in the previous videos or lectures I have explained that how the p orbital look like, and you know that they are perpendicular to each other, or if someone haven't studied, go and study the shape of orbitals in this lecture series, so you will come to know. 1p is, suppose this is pz, okay. Let me draw the coordinates, Cartesian coordinate system, okay. Suppose the above one, we say that this is z direction, this is the minus z, okay. This is say x, this is y, so this is x prime, this is y prime, okay. X, capital X, or forget about that, all are small, these all are lower case letters, so it is not capital, but I have written it. This is just x and prime x. This is coordinate system. So this is in the pz direction. In px direction, another orbital is there in the molecule. This is in p, and in py direction there is another one, okay. So they have directions with them. Why I'm writing that? Those it has some purpose or meanings, okay. Now what they say, what the experiment says, the p10 has 4 bonds, okay, that's good, and all the bonds are equal, okay, and have some angles with each other. So now there is one thing, that suppose one of the bond is produced between this hydrogen is attached to this hydrogen. This one hydrogen, suppose it doesn't have space, so one hydrogen is attached here, and the other hydrogen is suppose attached here, and now one hydrogen is attached here. These hydrogens are attached to different places, but as you know that the p orbitals, they are perpendicular to each other like this, okay. In the z direction, this is the x, the black one is the x, and coming toward you is the y, and this blue one is the z direction, okay. So automatically one thing is there, that the angles between those three hydrogens should be 90 degrees with each other, okay, because they are, suppose these are tips and hydrogens are attached to those tips. This one hydrogen will be attached to this tip, the other is to this, sorry, one hydrogen should be attached to this tip, the other should be attached to this tip, and the third hydrogen should be attached to the above this tip. So all the hydrogens has CH bonds have 90 degree angles to each other, okay. It is very difficult to handle them. Now suppose this is hydrogen, this the middle one is carbon, there is carbon and they are attached. Both those two CH bonds have 90 degree angle. And P, or what about S? Okay, in S you can arrange it in any way, because it is directionless. You can have one this, but in the P's you can either have one above or below, here or there, here or there. So what comes out of the excited state of this hybridization, that methane can form 4 bonds, okay. 4 bonds, 3 bonds are perpendicular to each other and they have some lengths associated with it, and there is a 4th bond. Wherever you want you can attach it, and that is because 3 are formed with the p orbitals. These are the p orbitals which are forming the bonds, okay. So let me write it like this. This is the p orbital forming the bonds. This is the p, okay, and it is forming a bond with hydrogen. This is another p forming bond, this is another p, and all of them are perpendicular to each other. Now the carbon has also an S. You can have a bond here, here, here toward you on that side, because H is sphere. And again, where is my favorite balloon? This sphere, it can make a bond here, 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 here. Okay, so you can make a bond here, but this thing seems to not is not coherent or similar to the experimental values. So it is not correct. This thing is wrong. Okay, so because we come out with a methane molecule which has 4 bonds. Okay, now let me write another bond here, and all the bonds have 3 of the bonds have 90 degrees angles with each other. 3 bonds have 90-degree angles with each other. This has another 90-degree with each other, and these two, of course, they have 180-degree each with each other. They have the same length though, but the s orbital is a little bit smaller, not that much smaller, but it's smaller than a double dumbbell, and this bond would be short. So here 2 errors arises in this methane molecule. Error number first: all bonds are equal in length. No, 3 are equal in length, but one is a little bit smaller. So this is one, and this is experimental or methane molecule. It goes against experimental evidences. Second thing is, because this is okay, the angle thing. Other thing is hydrogen. Okay, this is small bond, and the other are large bond. The large bonds. This is small bond, the other are large bonds. Okay, so again, this is not correct. Okay, number third thing is, all the bonds have similar energy. Yes, yes, yes. But what about hydrogen? Anything bonding with the 2s cannot have the same energy like with 2p, this, because 2s is a little bit lower in energy. Okay, so this theory is messed up, and it's this or methane is wrong, and this alone cannot do and form the bond. So when you excite the atom, it is not able to form a bond. Okay, so, and now what was there? Another thing, there was a scientist, his name was Pauling, and he proposed something. Which was very much important. Let me read his statement. He said that the configuration of atoms and the configuration of an atom in isolated form and the configuration of that atom in a bond are different. So let me put those in simple words. He said that the orbitals involved in a bonding are different than the orbitals which are present in an atom. In an atom, as we know that suppose in a carbon atom you have 1s orbital, 2s orbital, and 3 orbitals which are called as 2p orbitals. So this is atomic orbitals, but he said that those are different, and his statement has mathematical backing. I mean that his argument was backed by mathematics, high-level mathematics, and physics was involved. He came up with that statement, not just sleeping in the night and just wake up early in the morning and told people, okay, it should be different. No. He has some knowledge about this, and he proved that mathematically. Right now it's not in the scope of your course, and he used many equations. He knew the equations for one electron atom, that is quantum mechanics, so forget about those things. But right now we can say that the this is not good, or methane is out. Pauling says that those orbitals are different. Then the people or then the scientists come up with something else which is called as the hybridization. So as you know that in when bond is produced, so the orbitals all mix together and form overlap with each other, or you can say they mix together. Let me elaborate or simplify my statement. In hydrogen atom, there was a proton, there was one S, okay, and in other hydrogen there was a proton and there was one S, and one S has high electrons into it. Okay, this circle is 1s, this is nucleus, this is a proton, this is a nucleus, this is a proton, this is electron, and in that thing they say that we can say that those two 1s orbitals overlap with each other and form a hydrogen bond. Okay, and the electrons are in great motion, so they form a electron cloud between them. Okay, this is electron cloud between them. So this is what we can say that what a bond is. Okay, so here as you see that two orbitals of different atoms combine together and form a bond. Okay, but what actually happens in hybridization? So according to that hybridization, the orbitals again mixes with each other. These are the orbitals of different atoms. One is from one hydrogen and one is from the other hydrogen. This is hydrogen atom, but these are different atoms. But in hybridization, the orbitals of the same atom mix together and produced some other orbitals which are called as hybrid orbitals. Okay, so for organic chemists, you need to know some three types, that is Sp, Sp2 or Sp3 hybridization. Okay, so let me start those hybridizations. The first one is called Sp3 hybridization. Sp3 hybridization. Okay, what Sp3 hybridization is? Sp3. Okay, here one s orbital and 3p orbital mixed together and produced another orbital. Okay, but now why hybridization is used? Hybridization is used to define or to describe the molecules which are formed just like this. With the help of hybridization, this molecule this molecule can be understood, and the shape of this molecule can be justified or you can say confirmed. So there is Sp3 hybridization. Okay, in this hybridization what happens? Again we go for a carbon because we are studying a methane. So as you know, again to the classical thing, this is 2s, this is 2p. In 2s there are 2 electrons present. In 2p, sorry, the 2p is a little bit higher in energy. It has 2. Now it is a ground state. Go for the excited state. 2p, again I haven't written those, and this is the 2s. Again, what is in the excited state? 4 valence electron, sorry, before here 2 valence electron in the carbon are available, and here in the excited state 4 are available. But as we know, let me again repeat that this hybridization, what it does, it just expands the structure, the bondings and all the things of the molecule. Okay, so hybridization is a tool which can explain those molecules, that how that are or that may be formed. Okay, So, but scientifically, experimentally, with the proofs, with mathematical and physics background. So this is ground state, this is excited state. Now what they say that 3 of the p orbitals, they mix together with the 2s orbital and produced new orbitals. Those are hybrid orbitals or mixed orbitals, and they form the bonds. Okay, so in a great hurry I have to explain that. Okay, this is Sp3 hybridization. So as you know, okay, one thing is there, that why there is not 1s, 2s, p3, why 1s is not involved in hybridization, as the 1s is of very much low energy and it cannot be involved in hybridization in carbon and other atoms. Only hydrogen has only one s orbital that is involved in that can form a bond. Okay, in other molecules, in most of the molecules, just like these carbon, nitrogen, oxygen, fluorine, which we know, the 1s orbital is not taking part in the bonding. Okay, but when you visit the molecular orbital theory or some other theory, you will come to know that it really take parts in bond formation somehow. Okay, but again we need to be focused on the hybridization. Now it is a CH4 molecule we are studying. These are the 2p orbitals, this is the 2s, sorry, these are 2s electrons, and in what happens in the hybridization here, the 2s orbital, this 2s orbital, it mixes with 2p orbitals. Okay, sorry, 2p orbital, they are 3 in number, but believe me, they are in x, y and z direction. Okay, and as you know that first of all, the 2s, let me write the 2s outside. This is 2s, it has 2 electrons first of all, and after that one of the electron was excited and it went to the other 2p. Don't worry that whether it went to the 2p, x, p, y, p, z, forget about that, those all are same. Okay, so one electron went there. Now you have, now those orbitals mixes with the p orbital, this s orbital mixes with the 3p orbitals. So let me give you some values of energies. They are not real values, but that will help you, to make you understand. Suppose we have this s2s orbital has an energy of suppose 10, and suppose these are just values, these are not scientific or experimental, but just to make you understand. It has 12, one of the p has 12, other p has 12. Okay, as you know that these orbital mixes together, 4 orbital mix together, and it produce 4 other hybrid orbitals. Okay, 4 multiplied by sp3 orbital, they are produced. So let's see the energy of those orbitals. Okay, so for first kind you have these for first type, let me say that you mix these 3p orbital and 1s orbitals, and we get another orbital. So what their energy will be? Their energy will be a little bit above than 2s and little bit below than 2p, but how much? So to understand that, I have just written those values. Okay, so 4 orbitals are produced. Congratulations, 4 sp cubed. 4 means multiply by 2. Okay, multiply by 4, so you have 4 sp cubed orbitals. Now if you add those things, what? 12 plus 12 plus 12 and plus 10, and divided it by 4, because 4 orbitals are produced. So it has energy of 10, it has 12, 12, 12, 12, 12, 24, 20, 36 and 10, 46 divided by 4. 46 divided by 4 equal to 11.5. We are assuming. So why I have written this 11.5 and 12. So the each sp cubed, or sp3 orbital has energy of 11.5. That is much more than 10, and it is very much near to the p orbitals. 11.5 is near to p than to s, or near to 12 than to 10. Okay, so they have energy not in between them. It is almost like here. Okay, so those have this energy. Now coming to the shapes of these orbitals, what the shapes of those orbitals will be. As 4 orbitals combined together and 4 orbitals are produced. Now let's move to the shapes. Each orbital, sp3 orbital, has a shape like this. Okay, so you can see that it has 2 lobes. This is bigger lobe and this is a smaller lobe, but this smaller lobe is a little bit bigger because than this. Okay, why I'm saying you will come to know when we compare it with the other orbitals. Okay, this is sp cubed or sp3 orbital. Okay, but they are 4 in number. Okay, one thing is clear, all of them, because they are formed by blending or mixing of those orbitals, so all of these 4 orbitals has the same energy. So I need to multiply it with the 4 because 4 are produced. Okay, but how those 4 orbitals are placed in a space? Okay, because they are not 1, they are 4. They are not like this. They are not like this, that 4 are directing upward. As you know, that each one has 1 electron in it. Sometimes I am writing this with the half arrow and sometimes with the full arrow. Pardon me, but I mean the electrons. Okay, so 4 electrons in them. And as you know that when things with charge, if something has similar charges, they are very much near to each other. Suppose there is a middle atom and 2 atoms are attached to each other and they have 1 electron each. Suppose this is 1 orbital, this is the other orbital. Okay, and inside this 1 electron is present. Electron repel each other, so they will repel each other at a maximum of 180 angle. Okay, to be as far apart from each other. Positive, the same charges should be as far apart from each other as it is possible. Okay, so this is not the case. They are not arranged like this. How they are arranged? Again, in old physics or old theories of physics, they said that when something, suppose this is a carbon atom and it has 4 orbitals now. Okay, so those orbitals will arrange themselves in such a way that they are at ease. From at ease, I mean that they are as far apart from each other as is possible. So the only one arrangement is which we can think is this one, 90 angles from each other. But believe me that there is a better arrangement than that. That is called as the tetrahedral arrangement, and I have this model. Okay, it is tetrahedral. The 2 things are looking the 2 methyl group, the 2 orbitals are in the same plane and the other 2 are in the same plane. Okay, you can see it like this. Okay, so let me draw it on a board, that how those orbitals, they haven't formed a bond as yet. Okay, they are just hybrid orbitals, so they look like so what will be their geometry? The shape we knew, the energy, we also knew that all of them have the same energy, but how they are arranged in a tetrahedral arrangement. What is a tetrahedral arrangement? It is like, suppose, now as you see that those two are on the plane of a board. What does the plane of on the same plane mean? That if you have, suppose, a paper or something, I have this thing, so they are on the same plane, okay, you can see. But the other two, one is toward you, and the other is toward the board, okay. So to see this arrangement, I have to write it, I have to draw it. This is like, these two are on board, those two orbitals are on board, this is carbon atom, okay, and the other two, one is toward you, so it is written like this, pointing toward you, and the other is, this one is on the back side of the board, you can say it is like this, it is toward you, so it is bold, or it's written in bold, that you understand that it is toward you. Those two are on board, plane of board, the red one, look at them, and if I hold it like this, they lie in the same plane, and this one is towards you, and that is away from it. In real tetrahedron, because this is model made by me, all these orbitals should have the same angles, okay, this one and this one, this, so this is our tetrahedron arrangement, okay. So when you look to this tetrahedron arrangement, so all the orbitals in the methane are like present in a tetrahedral form. Look at this, this is carbon, suppose this is one orbital, let me draw it with red marker, this is one orbital on this plane, and this is the other orbital, they are on the same plane. Now it is very difficult for me to write orbital which is pointing toward you, this orbital is pointing toward you, and the other one is this one is away, but so this is the one which is toward us or toward you, so, and the other one is on the back, so the back one I should write it like dots, okay, and this one, because it is not possible to draw very easily on a two-dimensional board, three-dimensional thing, it also requires good art, so I should write it like this. This one is, this orbital is toward you, and this orbital is on the back side. So as you see, now 4 hydrogens are attached to it, to each one. One hydrogen, other hydrogen, the other hydrogen, and another hydrogen, okay. As you see that all the things are proved. Now I should write it like this, okay. They all have, this is the carbon atom in between, okay. So all the CH bonds have the same length, all the CH bonds have the same energy because they are formed, and all have the same shape, and all the angle between all of them is 109.5. so it is proved, the hybridization just proved the structure of the methane, that it might be it may be produced in this way. So after this we are going to study the Sp2 hybridization.